Hey guys, welcome back to the channel. Today we are diving into merge sort, a super efficient divide and conquer way to sort things fast and clean. It's like organizing chaos, but with logic. You will see why it's favorite in coding interviews and real world systems alike. Let's get a quick overview before we see it in action. Alright, let's break it down. Merge sort is a divide and conquer algorithm. Yep, it literally breaks the problem into smaller chunks. It recursively splits the array into halves until each piece is just one lonely element. Then comes the magic. It merges those tiny subarrays back together but in a sorted order. And here's the cool part. It runs it in O of n log n time, no matter the case, that is best, worst, or average. It's also stable, meaning it keeps equal elements in their original order. But it's not the in place, so yeah, it uses some extra space. Because of that, it's a solid pick for linked lists and large data sets. Now that you have got the gist, let's see it in action. Let's kick off the animation and see merge sort in action. First, we divide it into two halves, left and right. Then we keep splitting each half until every subarray has just one element left. Now comes the fun part, merging. We start merging the pairs while comparing and sorting. We start with 6 and 5. Since 6 is greater than 5, we take 5 first and then 6. And moving on to 3 and 1, 3 is greater than 1, so we pick 1 and then 3. Then comes 8 and 7. 8 is greater than 7, so 7 comes first and then 8. And finally 2 and 4. 2 is less than 4, so no change. We take 2 and then 4. Now we have got our first level of sorted pairs. Next, we merge those sorted subarrays into groups of 4, starting with 5, 6, 1, 3. Compare 5 and 1, take 1. Then compare 5 and 3, take 3. Now just add 5 and 6. That gives us 1, 3, 5, 6. We do the same thing for the next group. That is, we have 7, 8, 2, 4. When we do 7 versus 2, 2 is less, so take 2. 7 versus 4, 4 is less, so take 4. Then just add 7 and 8. That gives us 2, 4, 7, 8. And finally, it's time to merge the last two halves. Let's start with 1 and 2. 1 is less than 2, so we pick 1. And then 2 versus 3, 2 is smaller, so we take it. Then 3, then 4, and so on. We keep comparing the smallest remaining elements from each side and pick the smaller one every time. Step by step, the two halves merge into one perfectly sorted list. And just like that, we are done. Merge sort quietly does its job, efficient and clean. Now let's jump into the code and see how this all comes together under the hood. Alright, here's the code for merge sort function. We start with a simple base case. If the array has 1 or 0 elements, it's already sorted. So we return it as is. Next, we find the middle index and split the array into two halves, left half and right half. Then we recursively call merge sort on each half, breaking them down until we hit the base case. Finally, we call a merge function. We combine the two sorted halves back into one. This is a high-level recursion. Now let's take a closer look at the real workhorse, that is the merge function. Here's the merge function, the part that actually puts everything back together in a sorted order. We start with two sorted lists, left and right. An empty list called result will store our merged output. We use two pointers, I and j, to track our positions in each list. While both lists still have elements to compare, we check. If left I is smaller, we add it to the result and move I forward. Otherwise, we take right j and move j forward. Once one list runs out, we just extend the result with whatever is left in the other list because it's already sorted. And that's it. We return the fully merged list. Simple, clean, and efficient. And finally, we call merge sort on our unsorted array and boom, out comes the sorted result. Now let's check out how it performs. We'll look at the time complexity on a graph. Here's the time complexity graph for merge sort, running at n log n on average. That means even as your data grows, merge sort stays efficient and scales smoothly. Compared to simpler sorts like bubble or insertion sort, which can slow down to n squared, merge sort handles large datasets way better. No wonder it's a go-to choice for both interviews and real-world applications. Thanks a lot for watching, guys. Hope you found this helpful. If you enjoyed this video, make sure to hit the like button and don't forget to subscribe. I'll see you in the next one. Until then, keep learning, keep coding. Thanks again.